Well, to summarize what we learned in the one variable linearization, we call linear regression. I want to point out the linear regression typically used for two purposes. Number one is to use the data to predict the value is going to happen in the future. For example, if the manager tries to find out how much money I invest on the advertising and how much sale I can increase in the future based on the data I have, and then I'm not going to collect only two data. I'm going to collect 200, 2,000 to tell me that's the real work, and then to see if I need to invest more or less. The second purpose is to do a hypothesis test in scientific research. And you make some hypothesis and you see if this hypothesis is true based on your observation of the deviation and the data sigma in the statistics. So that's the idea to solve the overly determined system. When you have more equations than the parameter you have, we're going to see the least square, or say OLS, again and again in the future application. Now let's move to the next half. Now we move on to multivariant or multiple variable. Most of the time we call it multivariate regression. So let's look at another example. You might think, hey, the consumption of the chicken not only related with the weight of the chicken, maybe also related to the age of the chicken, the race of the chicken, and the weather, everything. So in the new example, you have more than one independent variables. So you still wanted to predict the food it consumed, the chickens consume. So instead of a straight line, if you observe two independent variables, let's say the chicken weight and the chicken age, then you're going to get a plane. You have the relationship like y equal beta 0 x1 plus beta 1 x2. And if you want to add another variable, let's say the temperature. In the winter, of course, they consume more food. In the summer, consume less. Then you might add the beta 2 x3. Can you see it now? You get a 3. Let me add another one, the constant. Get the 4 parameters and 3 different factors. So in this case, we got a so-called super plane. It's not just a 2D plane, but we call it a super plane. Anyway, the bottom line is they're straight. It's not a straight line, but the plane is straight, no curvature. So in general, you have n observations. That's the data set. I'm going to show you in a minute. And then you have m observations. M independent variables, n observations. And then the relationship we have instead of 2 columns, in here we get m plus 1 columns. That's the only difference, because your one data has 1 to m, because you have m variables. Let's back to the chicken example again. Again, could be the weight is 5.4, that's 1 input. And the age is 6 months. And the temperature now is 71 degrees. And then the first one, so in this case, you get a 4 by 10. The 10 is the observation matrix. And then that's the same. That's the error from your prediction model. Not much difference. All you need is do the least square. You square the area, and then square here. We write it into a matrix form. This is y minus x beta transpose times y minus x beta itself. And then you make this spread fact, just spread it, distributed with the FOIL. When you do matrix multiplication, what do you remember? Just don't switch the order. If you switch order, it does not make sense. When you take the derivative, you also have the product rule. Let's say you get 2 functions, a of t, a and b. If you take the derivative to t, now this is single variable, the same as the multivariables, you simply follow the product rule, take the first, and keep the second. Then you take the derivative to the second. And again, the only caution I warn you is don't switch order. Don't make the left to the right, right to the left. Everything else is the same. So we take the derivative to beta, which is a multivariable. You can take it to each of them. We got a gradient. So take this derivative, that's a constant. That's the data you have as output. And you take the derivative to beta, that's gone. The beta is derivative beta to beta is 1. Take a derivative to beta on the left, it's gone. And take this one, you need the product rule. You get it twice. Let me show you how to do it. You take the derivative to the first half, this one, and then it's going to be x prime, x beta. Beta take derivative itself. You take the derivative the next half to this one, is beta prime, x, and these are the same because the symmetry. That's why you get 2 of them. Now we set it equals 0. We know how to solve it. And well, let me see. The solution right here. And this is the estimate of the parameters. For the chicken example, I gave us 3 of them. So you get this equals 0, and that's straightforward. You just solve it. 2 cancel out the 2, x prime x beta equals x prime y. Now this is going to be a square matrix, and the square matrix is not a singular. And then all you need is the inverse on both sides, and then you do the inverse on the left sides. That's what you get on the right hand. So I will let you go to the detail. And then we look at the least square. We call it a residue sometimes, or sometimes we call it a variance. And this S, after do a little bit of calculation, you see is the square matrix of the y transpose. That's a row vector times the y column vector. So the y itself is n by 1. The transpose is 1 by n in the n. Of course, that's a scalar. It's 1 by 1. It's a number. So it's this one. And the x is n by m, and the beta is m. The y is n by 1, and then the beta is m by 1. Can you see it? Again, that's a scalar. So anyway, you get this residue. That's the total error. So we get the solution here. Maybe solve manually. It's only realistic when the m and m are small. But if it's big, no problem. You solve by the MATLAB and the software tool. That's what we use all the time. Let's look at this example. It's not about chicken. It's about the investment to the advertising, promotion, and look at the computer's cell, try to figure out the predictor, your own cell, based on the market data we collected. In here we have 15 data set, and that means our n, the observations, is 15. Well, our n in here equals 3, and our matrix is going to be a 15 by 4 matrix. Again, we use the keyword regression to solve it. And what's the output? Our y is here. It's a 15 by 1 vector. And then the relationship is, let me write the relationship. To put the x matrix, I only need to add all those 1 in the first column. Why I need to add the 1? Because you have this intercept beta 0, not multiply anything. Now let me try a little bit to show you why. The 1 is important. This is your x, and your beta is this beta 0, beta 1, beta m, and you see 1 times beta 0, that's the first one, 1.3, beta 2, that's the second one, and the third one, and the last one, now beta 3. That's how you need to add the 1.